Now we will explain the advanced differential module and how to test the transformer differential function using the CMC 500. Okay. First, following our Omicron-Ohm's law, we will start with the test object. Okay, for the REX640 relay. And as you can see here is a differential REU file. If you double click the differential REU file, it will give you some tips. We will explain one by one. For the first step is a protected object. So you have here some options to select transformer, generator, motor, or bus bar. Okay. And where is the line? If we have to select line to line, end-to-end, or line differential function, we will use the bus bar. Yes, exactly right. Because the bus bar, it has the same CT ratio in the local and the remote side. Yes. There is no any vector group correction factors, so it can be used as a line differential. Okay. So for now we have transformer. We have to specify this vector group. Now we have star 0 star 0, and also the number of winding 2 or 3. Now we have 3 winding, which is primary, secondary, and tertiary. If you have only 2 winding, primary, secondary, you can select 2 winding. Okay. Then we have the primary, secondary, and tertiary winding. You have to you can put a name here. This is the winding name or leg name. You can put primary, secondary, tertiary, or high side, low side, tertiary side, and so on. The voltage is from the setting 231 kV, 115.5 kV, 10.5 kV, and the power is 160 megavolt ampere, 118 megavolt ampere, and 42 megavolt ampere in the tertiary side. And here is the start point grounding for the primary side is not connected, not grounded. The secondary side is grounded, and the tertiary side is not grounded. And here is the current, which is the nominal operating current. This is the rated current based on the setting values, which is the power divided by root mean square of 3 multiplied by the rated nominal voltage line to line. So this can be calculated, and also it's here, it's really calculated for you. You can use it. Okay. Then this is the delta connected if you have any delta connection. Second step is the CT. Now you have to specify the CT ratio in the primary, secondary, and tertiary side, and also you have to specify the start point grounding. Is it towards the object or towards the line? And it's very essential in that case to calculate the differential current and to calculate the biasing current and how to differentiate between both of them. And also the connection. Normally the start point is towards the object most of the time, towards the protected object. So if we are protecting a transformer, so the CT start point from all sides, primary, secondary, should be towards the transformer. Okay, regardless of S1 or S2, but it should be towards the protected object, which is the transformer in our case. Okay. Then you have, if you have ground current connection inputs, if you have neutral CT on the for the secondary side, because secondary side have start point and grounded. So if you have neutral CT on this start point grounding, you can specify this neutral here, which can be used after that for the restricted earth fault for the secondary side. Okay. So if you unactivate this value, you will not be able to find or put any values here. Third step is the protection device. Here is the bias calculation, which we explain, and it differs from relay manufacturer to another. And you have to read the relay manufacturer user manual to find out what is the bias calculation formula used for this type of relay. Otherwise, if you don't have the relay manual, you can press the help button, and it will give you a guide of most common relay types and what is the used parameter value. For example, this I primary plus I secondary over K1 can be used for 7UT51, 7UT6X, 7UM62, and the K1 equals to 1. Can be used also for 7SCD5, 7SCD6, and 7SCDA. Can be used for SEL relays, some of them, and so on. Okay, and this constant can be changed from one relay to another. As you can see, K1 equal 1, K1 equal 2, and ABB relay also RET6115, 620 can use I primary minus I secondary over K1 and K1 equal to 2. And the maximum of I primary and I secondary can be used for RED 670, RET 670, 7UT 8X, and so on. So if you don't know, you can make double check also from the help button. Clear? So for our example, we are using this value for the REX 640, I primary and I secondary over K1 and K1 equal to 2. Okay. Here is the no combined characteristic. We can use this no combined characteristic in some cases in the ABB relays. As you can see from the help button, you can see the meaning of the no combined characteristic, as you can see here. So it can be used only for the in case of the ABB RET670. Clear? Okay. Otherwise, you can make untick because the RET670 have internal calculate this effect of single phase to ground fault on the other healthy phases, and it can subtract it from the relay itself. So there is no need to activate it inside the test option. Okay. So here is the meaning. we have also here the test time setting, and we can specify the maximum test time and the delay time. And this delay time, which is 0.25 second, 250 millisecond, is this the delay time between the two adjacent shots in case of you make dual slope characteristic testing using the shot mode. This is the 250 is the delay time between two adjacent shots, okay, to allow the relay to reset and to make the next shot. We have also the differential current setting. Here is the IDIF greater and the IDIF double greater. IDIF greater in our example is 0.25, IDIF double greater is 6. Also, we have the current tolerance in relative and in absolute, whichever is greater is used for the assessment. Also, we have the reference winding to be primary or secondary or tertiary. You can keep it as a default as a primary. Also, the reference current here, you have to choose from two options to the reference current to be the protected object nominal current or the current transformer nominal current. The main difference here, the protected object nominal current is the value here, which is calculated from the power and from the rated nominal voltage, but the rated CT current is 400. Okay. And there is something called the matching factor that depends on the rated nominal current and the CT ratio. We can calculate it also inside the test report. We have also the zero sequence elimination. If you have any start point grounded, you can select IL minus I naught, and it will subtract the effect of zero sequence component current from the differential current. If you don't have, you can select none. If you don't have any start point ground, select none. If you have a start point ground, but you use a star delta interposing transformer to eliminate the zero sequence component, you can select this option, or star delta star interposing transformer. But I think it's not available. It's not very common right now. It's old scheme. And also we have differential trip time setting. Now we have 0 second, or you can put it 20 milliseconds, 30 milliseconds, because you have to take in consideration the minimum tripping time. Also the time tolerance here in relative and in absolute values. This is a protective device tab. We will go for the second tab, which is the characteristic definition. Here, as you can see, the characteristic definition from point 1 to point 2. So you can define the start point here to the end point for the first slope. Then you have to define also the start and the end point for the slope 2. And then press add, click add, and it will be added like this. And once you move the cursor to this coordinates, it will give you the slope calculated from these two values. Now you want to make sure that your calculation is good. No need.
Okay.
It will cut the characteristic as the IDIF minimum for sure,
okay.
because you specify the IDIF minimum, and it will give you the dual slope characteristic as you see in the presentation, without specifying this point, actual point. Okay. Just draw slope 1 and slope 2, and it will cut as IDIF minimum and IDIF unrestrained. Clear?
Okay.
Then the harmonic. We have two options here, to second and fifth harmonic. For example, we have second harmonic at 20%. As you can see, here is a 20% of second harmonic waveform, referring to the fundamental waveform. And as you can see, below this value, there is no tripping at all. It's all blocking because it's below the minimum differential current. Okay. And above this value, which is ideal restraint, it will be tripped all the time, regardless of the amount of second harmonic waveform. Clear?
Yes.
And the same also for the fifth harmonic, but with a different percentage. As you can see, here is 45%. You can specify it as you like, and it will draw a line like this. And as you can see, this line also have a start and end point. So this start point is 0.25, which is the minimum differential current, and 45%. The end point is 45% also, but the I differential is 6. Okay, clear?
Yeah.
So this is the first part. Second part is to define the hardware configuration, as we learned from the Omicron Ohm's law. So, for example, I am using I primary and I secondary for two winding transformer protection. So I have to choose first the CMC. Now it's online. Then you can go for, here is the current output. You can make it 6 for two winding transformer, or you can make it 9 for for 3 winding transformer. But in that case, you have to make the voltage to be 0. Okay. But for our example, we have two winding transformer differential, so we will need only 6 current, 3 for primary, 3 for secondary. Okay. And here you have to define the I secondary to be from current output P, and I primary to be from current output C. And then you have to add the trip contact and so on. Then here we will start with the differential configuration module. Differential configuration module, we can use it for two purposes. The first one is to check the wiring check, and the second one is to check the stability check. Okay. So for example, we have here 3 winding transformer. As you can see, star 0, star 0, and this star 0 is grounding. So we can add 1 point or 2 points, like here. From here, you can add one at 1 IN. I will press add, or I can remove it. I can add a sweep of points, like from 0.25, which is the minimum differential current. I can make it 0.3, for example, or 0.5 up to 5. And the step size is 0.5. So I will have 10 test shots. I will add to the table. So it will give me some test points. And each test point, if you can see here, the primary and secondary values of the current is changing based on the I bias value there, or I test value. Okay, so I can keep it 1, yes, no problem. So we can keep only 1 point just to explain to you. And here you have to define the fault type, single line to ground, line to line, or 3 line. But here you are not allowed to make 2 tests in the same module. So you can make line 1 to ground, and then you can take copy from the module and choose a different fault type, line 2 to ground, line 3 to ground, and so on. We are allowed to do a fault type, only 1 fault type in the same module. It's based on the differential module structure itself. Okay, it's not like the impedance characteristic. Okay, so you have here to select which one you need to inject. So for example, I will select here 3 line. As you can see, here is the primary values and secondary values, and here is the external fault. This external fault is in the high side, on the primary side. Okay, but I can put it here. You see, this is the fault here in the primary side, and the supply coming from the secondary side to supply this fault current. But I can change it to be the fault to be the fault to be secondary and supply to be primary. Here the fault now is external, yes, but in the side of secondary, and the supply is coming from primary. And in both ways, if you are looking for the angle difference between IL1 here and IL1 here, it will be completely 180 degree, which means it's external fault. So the summation, vectorial summation of these 2 currents will be 0. Yes, because have the same value and in opposite direction. Okay, so here is the simulation of the external fault. So this is the test data. We have to specify the test shot, and you have to specify test point. Then in the test here you have to select, or not have, it's an optional to you can select the measured values to be primary or secondary, and it will allow you to put the measurement values here and to be printed out in your test report as an indication of the stability of the differential function. Okay, so you can express it in the primary and the secondary values, and once you click OK, it will allow you to enter these values here in the magnitude and the angle. Okay, or you can put it in a differential and bias, I differential and I bias for L1, L2, L3, and this is more convenient and more suitable for such test. Okay, here in the general mode, you can select from many more options like fault primary, supply tertiary, fault primary, supply secondary, and so on. And also, if you need to apply pre-fault, you can select and activate this apply I load as pre-fault current, and you can specify this pre-fault current to be 0.2 IN and so on, or you can unactivate or deactivate this I load to start directly. We have also here the test time. This test time is 60 seconds. This means the test will remain 1 minute, just to give you chance to check the measurement and to make sure that the differential no trip happen. You can increase these values. You can build 5 minutes, 10 minutes as you like. You can make it 1 minute. And it's sufficient for you to take the measurement and to check the blocking functionality of the differential trip. Okay. Then we have the voltage output. If you need to inject voltage, in our case there is no any need to inject voltage in this case. Here is the time trigger if you need like end-to-end testing for the line differential protection function. We have 2 CMC and we have time trigger using the CMGBS in local and remote substation. So we will apply this time trigger in that case with each CMC. So for example, I will apply the time trigger with primary side, and you in the remote side, you will apply it with the secondary side. Okay, and in that case, we have to apply the time trigger from the hardware configuration. As we explained here, you have to apply this time trigger from using the CMGBS 588. After you activate this time trigger in the hardware configuration, you will see it here. In the time trigger, this one will be activated to give you the chance to adjust the time setting and the time better for the synchronization of the CMGBS 588. Okay? But for sure, I think if you need to apply the time source, you need to apply it from the global hardware configuration. Okay? Then this icon will be visible for you. We are injecting in the primary and secondary side with the same CMC and the same device. So there is no need. Only the need in case of end-to-end for line differential function. We have to distributed CMCs in the local and the remote substation, maybe 100 kilometers away or 50 kilometers away for the overhead line. So I need time source to synchronize these 2 CMC together using this light and using the CMGBS. This is the only use case. Okay. Here you have to define the trigger condition to be with the trip contact for sure, and the binary output is no need at all in that case. Is that clear till now? So we can start this test.
Yes.
As you can see, there is no any differential happen. And how the test universe will know there is differential happen or no? From the trip contact. Yeah, from the trigger condition. Also, you can see it visually from the relay if you need to make more sure. For example, here is the transformer now.
Yes.
I am injecting now 3 lines.
Yeah.
As you can see, primary side is 737,
Yeah.
which is 1.84. 1.84 multiplied by 400,
Yeah.
it's 787. This is the situation.
Yeah.
And here is the I secondary,
Yes.
1475, because I am injecting 2.46.
Okay.
If you multiply 2.46 multiplied by 600, to give you this value. Okay? Clear?
Yeah.
So here is a measure. Now 60 seconds is done. Here, as you can see the screen.
Yeah.
Here I can put these values here, I differential and I bias. Because I select it.
Okay.
Yeah, I selected it already. So I can make I differential 0 I bias is equal to 1 I in and so on based on the relay measure. For example, I will just start again because the 60 seconds is done.
Maybe you can increase the time.
Yeah, we can. Yes, we can make it 120 or 300.
Yeah.
Yeah. Now 5 minutes. I think it's more than enough.
Yeah.
So we will start. For example, here in the test object, in the test car here, as you can see,
Yeah.
here we have some values. Yes.
Yes.
Here is I primary and I secondary. I can put it here in the I primary and I secondary.
Yes.
To be printed out in my test report as an indication there is no trip happen.
Yeah.
And also the I differential and I bias, you can see here the I differential is 0, the I bias is 1.84. So for example, I will edit one example for you, 1.84, 1.84, 1.8. Okay?
Yeah.
Then I have to select the assessment now.
Oh.
Since there is no any tripping happen,
Yeah.
there is no any trigger option using the trip contact, and I didn't see any trip happen, so I will click pass. See the test report now. Here is the I differential and I bias which I already entered.
Yeah.
Whichever is sooner,
Yeah.
the time is elapsed or you select pass.
Yeah.
So if you put 60 seconds, but after 10 seconds you are make sure, because it's happening instantaneous.
Yes.
If anything happens, it will happen instantaneous. It will remain for 10 seconds. It will not remain for 10 seconds.
Yeah.
So, but if you need more time for putting this measurement for to be printed out in your test report, you can do it. Okay. This is, for example, this is a line 3 line. For example, we can do the same for line L1 to L, because the name of the file is here is L1 to L, so we can keep it as it is, and we will add here. See the IL1 values here and here, and IL2 and IL3.
Yeah.
You can see the difference. You can see here the measurement right now. Here the IL1 is 492.
Yes.
Because here it's 1.23 billion.
Yes.
Okay. And IL2, IL3 is affecting, yes, for sure. And the other side, in the secondary side, which is the faulty side, IL1 only 2.46.
Yes.
Which is 1,475. And here's the I differential, as you can see, all 0. I bias is 1.23, 0.61, 0.61. So I can enter this values. In the test is 1.23. Yeah. Yes.
1.23, 0.61.
Yeah, it's half the value. 0.61. Yeah. And then I will select this. If you like to put it, you can put it. If you like to take a snapshot and just paste it in the test report, it will be printed out.
Yes.
As you like. Yeah. This is an option.
Yeah.
Okay. So this is the first part, which is a differential configuration module.
Yeah.
Okay, we can do the same also using the line 2, line 3, 3 line, and so on.
Okay.
For example, we can do one more time for the line to line,
Yeah.
just to see the effect of the asymmetrical components and the line currents. So here is line to line, L1 to L2 full type, and 2.5 IN.
Yes.
You can remove it and make it 1 IN, for example. It's enough. When we, yeah, 1 IN. See, now IL1 and IL2 in the primary side will be 1 ampere and 180 degree, 0 degree.
Yes.
Here in the secondary side, 1.33 ampere. Here is the because of the vector group and the protection factor and so on, and many factors it will affect this. So 1.33 here in the secondary side shows the I differential now equal to 0. Okay,
Yes.
and as you can see, the phase shift between IL1 here and IL1 here is 180 degree, and IL2 here is 180 degree.
Yes.
Yeah, but because it's line to line, so the IL1 is in the opposite direction of IL2.
Yes.
It's returning in the IL2.
Yes.
So it's line to line fault.
Yes.
It's not the same as line to ground fault. Okay, and we can start. We can take the measurements as well. We can put it in this. Right. So here is 400, because one IN.
Yes.
And here is 799 and 800, which is 800.
Yes.
800 is 1.33 multiplied by 600.
Yeah.
Okay. So you can enter this value again, or you can enter it in I differential and I bias. You see I differential and I bias. I differential is equal to 0.
Yeah.
I bias for L1, L2 is 1, and the other is 0. So I can make it here 1. Then I will click pass. Clear?
Yeah.
This is another example for L1, L2. We can move forward for the next module.
Yes.
to save our time.
Yes.
So the next module is the differential operating characteristic. This is very important also in our cases. So here is the differential operating characteristic in the other screen. Now, now it's visible. Here is the pink one. Did you know what is the pink indicates? Yeah,
It has shifted the characteristic.
yeah, it's the zero sequence elimination and the combined characteristic effect. Yes. Okay. So if you are choosing like 3 line, you can see there is no any
There's no-
effect of
yeah.
zero sequence elimination. Okay.
But for
Because
single phase, it's
For
there.
single phase, yeah, the zero sequence elimination, it will be appear. You don't have to check. It will
It
be
does automatically.
it will be automatically detected.
Okay.
But if you need to make sure, here is the secondary side. We define star point grounding here.
Yeah.
So that's why we put it.
Oh, okay.
We put
it's
here
just
the
automatic.
I elements, I not for zero sequence elimination.
Okay.
So if you are, if there is no star point grounding and there is no zero sequence elimination, the line to line will equal to line to ground exactly.
Yes.
No any effect.
Yes.
Okay.
Yes.
This is the main parameter affecting this values.
Yeah.
Clear?
Clear.
So for example here, I can leave it line 1 to ears
Yes.
as it is. Let me explain first. Here is the fault type, 7 fault types, as the same as the other. Here is the resolution in IN, absolute value, and relative value. The resolution is the meaning between the distance or the step size between two adjacent shots. There is a resolution of checking. Okay, and this, if the result is not changing in this resolution tolerance, it will be submitted as this as final result. Okay, so it will keep searching until the protection relay decision not change in this resolution level,
Okay.
which means 10 milliampere. If so this one is the characteristic. Okay. This one is the lowest characteristic. So it will assess the result based on that.
On the resolution.
Yeah. And here we have two modes. Search, as we explained.
Yeah.
So it will search about the intersection between the search line and the dual slope characteristic boundary, and the shot mode, which allow you to add some test points here.
Yeah.
But for sure, here also the same. If you are doing the search test, you are not allowed to do any shot. So you can take copy and you can put some shots. Okay. So let us keep it here in shot, and we can take another example in shot. Yeah. So here is the general. Here, if you select ignore nominal characteristic, as you can see, here is the I differential nominal based on the nominal characteristic. If you activate this ignore nominal characteristic, here is the I differential nominal is not applicable, and it will allow the CMC to search to the boundary itself if you are not sure about it. Yeah. But for normal cases, you have to deactivate this normal characteristic to allow the CMC to assess the result based on the nominal values, based on the equations and the mathematics. You know?
Yes.
And also we have here the test for fault primary, supply, secondary, and so on. Here is the pre-fault. If you would like to apply a pre-fault for you have to specify a pre-fault current and the pre-fault time in this pre-fault stage. Because some relays need to sense the pre-fault before the fault state happens. In some cases, but in most common cases there is no need. Here is the voltage output if you need to apply a voltage output for any reason. And here is the time synchronized, as we explained for the line differential end-to-end testing. And here is the trigger condition. The binary output is not needed at all. We can start. You can add more points. You can add sweep from here, like from 1 IN up to 6 IN, with step size 1 IN. So it will give you sweep directly.
Yes.
Or you can add manually 1 by 1 as a search ramp, and as you like. You can add more points as well. And we recommend in Omicron to add at least 2 points per each slope.
Yes.
Yeah. So if you have slope 1, slope 2, each slope, at least 2 points, one in the beginning of the slope and one at the end of the slope to cover this area in between, in between first and second slope. At least, yeah.
Doesn't matter.
There is no book or the standard tells the user to test this kind of rotation function, you have to make like this. But just we give you a recommendation.
Yeah.
So if you have two slope, at least to put one point in the beginning of the slope and one point before the end of the slope,
Yes.
to cover the in-between region. Not also about your time,
Yeah.
because this test takes time.
Yes.
And there is a line-to-line characteristic. As you can see, there is no any effect of the zero sequence
Yes.
characteristic.
Yeah. So
Zero
it's
sequence is
straightforward.
yeah. So this is line to line. We can do also line. Here is the 3 line. We can do also line to line. Here I can remove. Let us remove all and use the same recommendation. So I will put two value for each slope. Okay. 2 test points. And here also I will put one for the unrestrained. Now I covered all the double slope, yes?
Yeah.
This is the search test. We will do the same also using the shot test.
Yeah.
At least one full time. I will show you what's the difference. Shot test for sure is more quick than more faster than the search test. Okay, so here is the line to line using our recommendation for the test shots. But as you can see here, the report view doesn't have the characteristics, so we can add it from here, from define, and go to the test result. I will add the graph to be printed out in my test report like this. Okay, it will be very look nice in my test report and give some luxury to my test report. Okay, now we finish this by using the search RAM. I will make copy and paste, and we will use now the shot test. Okay, for the 3 line again. So here is a 3 line. We can remove all the search ramps, and I will go for the short test. I can select the 3 line characteristic, and I will add some points here. You can press add like this. You can add this point here. If you press shot at this option, it will inject directly and give you the trip time like this. Just if you need to make a check, okay. But if you need to add a lot of and multiple shots, you can add the other option. Okay, from here add test points. So you can add higher than the tolerance and lower than the tolerance.
Yeah.
But don't add test point inside the tolerance, because this tolerance it will be assessed as pass regardless of the result of tripping or not tripping, because it's inside the tolerance band. You know.
So there's no need.
Yeah, just above or lower the tolerance dash lines. Okay, then you can press start. There is a lot of points here. The nominal trip time is no trip, as you can see from here. You see? The expected is no trip because it's below the dual slope characteristic. If any trip happens here, it will be assessed fail.
Yeah.
But for the no trip, it should be no trip.
Yeah.
because it's below the dual slope characteristic for sure.
Yes.
If any trip happen with any time, it will be a seized fail.
Yeah.
Because it's supposed to be in blocking zone,
Yes.
not operating zone.
Yes.
Is that clear?
Yes.
Now we finish the third one. We will go for the harmonic restraint. We have two harmonic restraint, second harmonic and fifth harmonic. We will do the same. We have also two test modes, by search and by shot. We will do by the same. So we have here search mode at 0.5 IN and 1 I differential over IN. Okay, here is the 20%, which is the setting value of second harmonic content.
Yes.
Regarding referring to the fundamental waveform. And here is the ID minimum. Below this value, there is no tripping, it will be in the blocking zone. And above the ID unrestrained, which is 6 IN, it will be direct trip regardless of the percentage of the second harmonic waveform. Okay, you can add values from here, or you can add sweep from value to end value with a step size, and then click add to the table, or you can remove all and add one by one. Okay, you have here different fault types: L1, L2, and L3, and L1, L2, L3. Okay, then we have also the shot mode. You can add some test points here and test points here to check the effect and the relay feedback. And the general mode in the same also. I think we explained it before. And here is the post fault to simulate a post fault state or a post fault current if you like. But in our case, there is no need. So in the search line, I will make it at 0.5 and 1. We can also make one more at 3, for example. Then at 3, so we will search here as well. Okay, then let's see. So here it will make the search to check the blocking and tripping feedback from the relay. So after exceeding this percentage, it will be blocked. Then it will get back to check the trip. Then it will go approaching the search lines, the boundaries, until it gives you the most accurate percentage. Above this percentage, it will be blocked zone. So as you can see here, this is the actual IXF over IDiff compared to the I nominal, which is 20. Okay, and now it's 1994.
Yes.
As you can see here. Okay, so we can do the same, but not with searching. We can do it by shot. So we can make copy and paste. So we can remove all of this search list, and we can add some shots here. We can add one also here under the IDiff minimum. And as you like, okay, you can do it like this. I think it's enough. So you can toggle between the second and the fifth harmonic from this field. We will see it in the next module for the fifth harmonic. Here is the fifth harmonic. As you can see, if you select second, it will be 20% second harmonic. If you select 5, it will be fifth harmonic directly. And in the same values, we can select. Okay, now the CMC will superimpose a waveform at 300 hertz. If you are using 60 hertz power system, fifth harmonic means 300 hertz will be superimposed. But for our case in Bahrain, we have nominal frequency is 50. So now we are superimpose a second waveform with frequency 250 hertz on the fundamental waveform. Okay, without any rewiring, without any reconnection. Just you have to select the values, and it will be implemented from the CMC to the machine directly. Yeah, here is the actual value 45.17, and the nominal value should be 45. Yeah. For the report view, if you need to select, need to see the report view. Here is the report view. If you need to print out the characteristic, you can print it out from here, and you can check the graph. Activate the graph to be printed out here. Okay. So I finished here. Maybe we have one more, which is a differential trip time characteristic. It's more than easy. We can put it here at the end. So here is the minimum and the maximum trip time. We can add some points here at 1 in. Okay, we have to define the binary input for sure to detect the trip time. Yeah. Okay. Yes. Okay, here is a 39 milli, 38 milli, 37 millisecond. Here is the trip time. This is the fourth module. Now we finished the fourth test module for the advanced differential. Trip time, characteristics, wiring check or stability, and the harmonic restraint. Okay, thank you for